Hi, this is Remembering the Past, the show where we talk about people who died recently who've had a profound effect on our history, our society, or our culture. And in our ongoing series on Nobel Prize winners, tonight we're going to talk about Dr. Burton Richter, who died recently at the age of 87. Dr. Richter was awarded one half of the 1976 Nobel Prize in Physics, along with Samuel Ting, for their pioneering work in the discovery of a heavy elementary particle of a new kind. He was a physicist working in experimental particle physics at the Stanford Linear Accelerator Center at Stanford, which we talked about when we did the Richard Taylor podcast. By about 1970, a large number of elementary particles had been identified. Most of these comprised 2 or 3 quarks. Using high-energy particle collisions and independently of one another, in 1974, Dr. Richter and Dr. Ting discovered a new heavy particle known as the J psi, proving experimentally the existence of a 4th quark, later named charm. Okay, it's experimental particle physics, so you know I don't know what I'm talking about, but I'll read from the press release from the Nobel Committee. The prize was awarded for discoveries in the exploration of the smallest components of matter, smaller than atoms and their nuclei. According to Einstein's well-known law of energy and mass, E equals mc squared, a large amount of kinetic energy are required to create a heavy particle. In addition, the energy must be concentrated. The 2 prize experiments were made independently of one another at 2 of the world's largest particle accelerators. Richter and his co-workers had their equipment connected to a 3-kilometer-long linear accelerator at the Stanford Linear Accelerator Center. It was so large that it could not be kept indoors. When exploring small objects, large microscopes are necessary and cannot be avoided. For the smallest bits of matter, the largest installations are required. The Richter equipment is sort of a carousel storage ring where a stream of electrons and a stream of positrons go around in opposite directions at very high speeds, which may be adjusted exactly. In head-on collisions, all the energy of an electron and a colliding positron may in principle give rise to a motionless, very heavy particle, which is expected to turn into several other particles by decay in a very short space of time. It had not been forecast that anything like that could possibly happen other than at low energies where the known lighter elementary particles exist. The research program therefore concentrated on following up in a specially built magnetic detector, a very interesting and significant line initiated at Frascati, Italy, and continued at Cambridge in the United States. The discovery of the new particle was sudden and dramatic, although preceded by years of planning and preparation. The speed at the head-on collisions may be adjusted to more than 1,000 different values. The new particle appears at only one of those values. About November 10, 1974, the Richter team set the correct speed and found that an enormous number of collisions gave the new particle christened psi. What was most remarkable was that the psi particle was transformed unexpectedly sluggishly, or in other words, it lived about 1,000 times as long as it reasonably should. Ting's team did their experiments in the Brookhaven Laboratory in New York, where they found a new particle and they christened it the J particle. On November 11, 1974, Richter and Ting met at the Stanford Linear Accelerator Center and found that the 2 research teams had discovered the same particle. The announcement appeared at once in the scientific publications within a week. It was dubbed the November Revolution. Burton Richter was a nice Jewish boy born in Brooklyn. Before moving to a private school in Pennsylvania, he did 2 years of high school at Far Rockaway High School in Queens. That high school is now closed, but it produced 3 Nobel Prize winners. Besides Dr. Richter, it produced Barry Bloomberg, whose podcast we've done. He won a Nobel Prize in medicine, and it produced the immortal Richard Feynman, who we've talked about in a lot of podcasts. Here's a clip on Burton Richter and his evolution as a scientist.
It was the sky. I was 10 years old. And in 1941, World War II started. New York was blacked out, and you could see the stars, and it was unbelievably beautiful and mysterious, and I wanted to know all about it.
Burton Richter, that boy from Far Rockaway, Queens, would unlock the mysteries of the smallest particles and contribute to our understanding of the theory of almost everything.
In the early part of the 60s, people kept discovering new particles, and the number of so-called elementary particles climbed and was approaching 100, and everybody came to the conclusion this couldn't be right.
These 100 plus particles were actually combinations of even smaller bits, known as quarks and leptons.
The thing that made me famous and Sam Ting famous is that in 1974, we discovered a particle that was not allowed to exist by the model we had at the time. There was something more.
Richter and Ting's discovery of the J-psi particle became known as the November Revolution. Awarded the Nobel Prize, their discovery advanced the theory of the standard model of particle physics.
I always thought about what the physics was and what I needed to do. I needed the colliding beam machine. So the SPEAR facility was very important, and I led the construction of the machine as well as the experiment. The legacy of SPEAR turned out to be much more than just this one particle, because in the next year, another totally unexpected particle was found, which also earned a Nobel Prize.
Richter continued at SLAC, this time becoming its director in 1984.
What the real issue for a laboratory is not only what it's doing now, but what it's going to be doing 15 years from now. Science evolves, and what is going to keep your laboratory as one of the leading laboratories in the world?
Under his leadership, SLAC evolved into one of the leading labs of the world in X-ray science.
I have a trajectory from active researcher in high-energy physics to laboratory director to energy guru. In the climate and energy business, it is essential that the public understands it. The thing that makes it hard is that it's not going to bother me. I'm 83. It's going to bother my granddaughters. And I think that the notion that we leave these kinds of problems to our grandchildren is just really a terrible idea, and it's unworthy of us.
In the 1950s, Richter went to MIT and was then recruited to go to Stanford and work with Wolfgang Panofsky. Wolfgang Panofsky was a brilliant German emigre whose father was a friend of Einstein, and Panofsky oversaw the construction of the Stanford Linear Accelerator Center in the early 1960s, as described here by Richard Taylor, one of the physicists who won the Nobel Prize at Stanford in physics.
SLAC started, the big accelerator at Stanford started, I came. It was on the way before I came home from France. I knew that it wasn't voted on in Congress, but it was earlier than that Eisenhower. Yes, it was, because Eisenhower is the one that brought it up, and he was gone by 1960. So it actually was 59 through 62. The final approval came in 62, but it was known that everything was going in 61. It was going to be the most expensive accelerator ever built. There's always been a split between the East and the West in the physics community in this country, starting with Lawrence and Rabi across the country, and then I think the Easterners didn't believe when the boss here, Panofsky, realized that the government might be good for $100 million.
Berkeley had been the center of physics on the West Coast. Interestingly enough, Panofsky came from Berkeley and became a fixture at Stanford for nearly 5 decades. One of the reasons he left Berkeley was because of the anti-communist hysteria there in the late 40s. Anyway, you heard Dr. Richter talking before about SPEAR. That was the Stanford Positron Electron Accelerating Ring that he developed when he was at the Stanford Linear Accelerator Center. Here, Dr. Richter talks about his groundbreaking work at SPEAR, and he alludes to Robert Hofstadter, who won the 1961 Nobel Prize for his work on atomic nucleons, and he mentions the LHC, which is the Large Hadron Collider, currently the European Center for Research on Particle Physics.
This was big news. It's very rare that an experiment changes the course of a particular field. This one did. Everybody knew that the then standard model, the old quark model, if you extended it to high energy, had real trouble, and nobody knew what the way out was. There were all sorts of models about the way out. And then this discovery was of a particle that shouldn't have been there. When I talk to kids, I use the kids' nursery rhyme. One day upon the stair, I met a man who wasn't there. He wasn't there again today. I wish that he would go away. Well, we found the man who wasn't supposed to be there. Before that, the old three-quark model had quite successfully predicted all the particles that were found, and had never predicted one there was never one found that wasn't includable in it, but this one couldn't fit in that model. So this was the smoking gun for what's beyond the standard model. That should be a very familiar phrase with you, because that's what people are talking about for the LHC. What's beyond the new standard model? And the old standard model fell then. The new standard model was on firm grounds. This was in 74. By 78, the new standard model was completed. Everybody's been trying to find out holes in it. And people find things that are not in it, but where you can patch it up and accommodate this phenomenon. Nobody's ever found something which is forbidden by it. And so people are still looking. All the attempts have failed, and the LHC is the latest attempt. I had a different idea. I wanted to know about the structure of the strongly interacting particles. Hofstadter had done the proton. Proton is stable. You could do that. I had fiddled around with the electron. I had done pair production. We'd do annihilation. We'd find out whether there's structure to the electron. But electron-positron annihilation could give you information about the structure of anything that could be produced. I was a not bad theorist when I was younger, and I had worked out, I think it was in 58, that this route could be very fertile in finding what I called the comparative size of all the different particles. Hofstadter had an RMS radius of the proton. Well, I could get the pi meson and the k meson and all the other mesons and the proton excited states, and I could find the form factor for all of those. That's what got me to building it. Did I expect that we'd find the fourth quark? No. But was I looking for the structure of the hadrons? Yes.
I'm going to close with a brief humorous story that Burton Richter told about his early days working at Stanford and a trip to New York City.
I did the first of high energy for the time tests of quantum electrodynamics, good enough to get me invited to the New York meeting to give an invited paper 2 years after I got my PhD. It was really pretty funny. My father, who was a New Yorker, went to this meeting. The first speaker was Bob Hofstadter, and Bob Hofstadter was talking about his measurements of the proton size. It was in the biggest ballroom of this hotel. It seated 3,000 people, and every seat was taken. And he gave his talk and all of that, and then the chairman called on Dr. Richter, not Professor Richter, to give his talk. 2/3 of the audience got up and walked out. And there's my father sitting in the back, fuming. And I gave my talk. And then I went to say, and he told me, how could they do that? How could they be so polite? I said, Papa, the miracle is that 1,000 of them stayed, not that 2,000 of them left.
The lecture that those 2,000 scientists left was ultimately the work for which Burton Richter was awarded the Nobel Prize. Well, I'm going to close on that note. I want to thank my producer and IT genius, Sid Tepps. As I said, Burton Richter was a nice Jewish boy from Brooklyn, and he went west. And as a final tribute to Burton Richter, we'll have another nice Jewish boy from the East Coast who went west and found fame. In fact, when he sang the song, he was one of the most famous men in the world. So here is Al Jolson singing California, Here I Come.
California, here I come, right back where I started from, where bowers of flowers bloom in the spring. Each morning at dawning birdies sing, and everything a sun-kissed miss said, don't be late. That's why I can hardly wait. Open up that golden gate, California, here I come.